This lecture is going to get us started with the topic of engineering economics. And engineering economics is a method of arriving at a preferred alternative when looking at typically it's with multiple design alternatives, where you have a particular, and in particular, it's done for large projects where the costs and benefits are played out over an extended period. So the time value of money, which we're going to be talking about, becomes kind of an issue that needs to be addressed. All right, so this is just kind of a typical type of problem that you might deal with, and I'm just going to introduce this as a way of introducing the topic. So imagine that you have ferry service. Ferry essentially is like a small boat that carries cars and people and produce or products across a river or a lake or any other water body and shuttles them back and forth. And years ago, before a lot of our river or water bodies were straddled by bridges, ferry service was typically, a kind of a typical operation. And sometimes in rural areas, you still see these kind of services out there. So the question is, in this particular case, is should we replace the ferry service with the bridge? And imagine that you have 1 million persons per year crossing over the bridge, say 10,000 trucks per year over that same time, and that the average transit time is a half hour. Well, looking at it this way, obviously, throwing a bridge over the water body, it's going to reduce the transit time to a matter of, a few minutes, and you can imagine the convenience and the amount of time saved. And if you could put a dollar value on the individual's time, that it's kind of a no-brainer, you might think at first, that we should definitely put a bridge up there. But obviously, engineering is more than just what's technically feasible. We need to think about the economics of it, whether it makes sense economically to construct the bridge and replace the ferry service. So I'm just going to make up some numbers. Imagine that you have $10 per hour is the value to individuals in their saved time. The value to business for our truck drivers, we'll say, is on the order of $50 per hour. And now we can begin to quantify the benefits. So this is an annual benefit. In this case, you do the math, you end up with $5 million annually for individuals, and then $0.25 million for business. And you might imagine there are other potential benefits that might accrue. And that might be reasons for constructing this bridge, but we're just going to leave it at this for now. So the costs, again, I'm just making up these costs. Imagine we have $100 million design construction, and then maintenance on the bridge is initially going to be 0.1 million or $100,000 per year, and it's going to grow at a rate of $100,000 per year because, as you can imagine, as the bridge gets older, the maintenance costs are going to be going up. So these are all our benefits and costs. And on kind of if you didn't know any better and didn't realize that the value, you need to consider the time value of money. You might just add up all the numbers and come up with, here's our benefit. I added up the benefits. We have 157 million. The costs are 146.5 million for design construction. And then I just took all these numbers and added them up together. But in fact, this is naive and this is not typically how things are done, because over a 30-year project life, you need to consider the time value of money, which I've been talking about now for a little time. And you also need likely to compare other alternatives. So let's look at what I'm talking about. So for example, you need to account for timing of costs and benefits. And it's the case that $1 in the future is less valuable than $1 today. And that may not seem obvious to you. You might think, well, if I have $1 today, or if I have $1 30 years from now, it's still $1. And it doesn't really matter. But when you start comparing them, you're really comparing apples and oranges. Not good. We're going to talk a little bit more about that in a future lecture. You also need to look at, oh yeah, well, this just says that the value of future benefits and costs need to be discounted. In other words, that value of that dollar 30 years from now is less than, if you think of it at its present value is less than a dollar. So costs are typically loaded toward, in this case, the costs are loaded towards year 0. Most of the costs were associated with design and construction. Benefits are in the future. So those benefits are going to be discounted, the costs less so. So that's going to influence whether the benefits are going to outweigh the costs. And you might need to consider other alternatives, size of the bridge. You want a big bridge, a small bridge, a tunnel, highway. Maybe there's an existing bridge down the road. You could run a highway there. Or maybe you just need an improved ferry service to make it. So you may want to look at what is the preferred alternative by looking at multiple alternatives. So those are the two things: cost of money, or the time value of money, and looking at alternatives that make that sort of naive approach that of just adding up the costs, adding up the benefits, and leaving it at that. And I just want to point out a couple location, or a couple of type projects recently that I'm aware of where this type of approach, engineering economics, was an important part of evaluating alternatives. And the first of which, this just came out October 2019. See a draft, they call it a major rehabilitation evaluation report. They're looking at the Bourne-Sagamore bridges that carry people to Cape Cod. If you've ever taken them in the summer, I didn't even notice. Here's the other bridge. I forget which one's which. Here's one bridge here in the distance. Here's one close up. That's a very nice picture. If you ever been to Cape Cod, you realize the capacity is definitely deficient. People are always waiting in line to get across the bridge. These are old bridges. They're on a neighborhood of 80 years old. So we're going to have to do major rehab anyways, and there is always ongoing maintenance. So this U.S. Army Corps of Engineers is a organization. It's done a lot of work, dams, bridges, canals, that are owned by the federal government. So they were basically took on this task of looking at these alternatives. And at least in their draft, you can see here's a photo from Boston Globe. It says Corps of Engineers calls for replacing functionally obsolete Sagamore-Bourne bridges. And they did look at other alternatives. They looked at what you'd call fix as fails. That's kind of what we do now. If it fails, we fix it. If it fails, we fix it. Major rehab is alternative 2. Replacement of the bridges with one bridge or maybe 2 bridges, a tunnel. They even looked at closing the canal and constructing a highway. This is not likely to go anywhere. And in fact, that wasn't the anywhere near the preferred alternative. The other system, or other engineering economics study, and here's a link to it if anybody's interested, is on the feasibility of harbor-wide barrier systems. These are basically systems to prevent storms, surges from inundating downtown Boston. It's done by the UMass Sustainable Solutions Lab with help from Arcadis and Woods Hole Group. And this is just a map showing flood extent, 10% flood extent. So essentially, I believe, you know what, I'm not sure, flood probabilities. Yes, that would be 5 foot. I think these are like once in 10 year, anticipated by the year, some future year, year 2100. So these are not really acceptable. Obviously, downtown area to have it flooded once in 10 years, not acceptable. So people are looking at different barrier configurations. One was this kind of what's called they call it Metro Boston Dike Barrier. This would be a huge, tremendously large project, basically to block out the surges that might be coming in from the ocean. There's a second, more modest, they call it inner and outer harbor barriers. And then they're also looking at a sort of an inner harbor barrier alternative. Um, and the Metro Dike barrier, that's this outside one. We're talking about $35 to $85 billion. And the shore-based strategy that's being looked at is kind of a modest approach of seawalls and building up the flood barriers in low-lying areas, flood-proofing buildings, doing other sort of local impacts on a shore-based strategy. In fact, that shore-based strategy was the preferred alternative in this case. So we're going to look time value of money, calculating present value, and creating cash flow diagrams in the subsequent lectures.